let's talk about the section 7.4. We'll talk about the trigonometric form of complex numbers. We know in the set of real numbers, this equation x squared equal to -1 has no solution, right? Because for any real number a, the square of this real number is always non-negative, right? So that means x squared plus 1 is always greater than or equal to 1, cannot be equal to 0. So this equation has no solution in the set of real numbers. But we can expand this set of the real numbers to a big set. Okay, so right now we expand this R to a big set. This is a set C. It's called the set of complex numbers. Okay, later we'll define. Actually, we review how we define complex numbers. So we learned this in the Math140, right? So in this big set, this equation has solutions. One solution is called the I. So let's plug in this I into this equation. Then we have the I squared equal to -1. So this I is called the imaginary unit. Right? So its square is equal to -1. And also this equation has another solution, -I, because the square of -I is also equal to -1. Right? So in this way, this equation has two solutions in the set of complex numbers. Then after we define this imaginary unit, we can define a complex number. So a complex number is just expression of this form, a plus bi, where a and b are real numbers. And this a is called the real part of this complex number. And this b is called the imaginary part of this complex number. So now, given such a complex number, we can uniquely determine an order pair. Okay, we have the a plus bi, then this guy uniquely corresponding to an ordered pair AB. Given an ordered pair AB, we can uniquely determine such a complex number. So that means there is 1-to-1. Okay, this 1-to-1 means 1-to-1 correspondence between the complex numbers and the ordered pairs. So we have the 1-to-1 correspondence between the complex numbers and the ordered pairs. We know an ordered pair is just a point in the rectangular plane, right? So right now we can draw such a rectangular plane. And then we can locate one complex number by using its corresponding ordered pairs. So we have the C point A here, point AB. And then this guy just corresponding to the complex number A plus BI. Okay. So this plane is called the complex plane. Because it consists of all those complex numbers, right? Each point is just a complex number by using this one-to-one correspondence between the complex numbers and order pairs. And this horizontal axis is called the real axis. Because on this horizontal axis, we just have the real number. For example, you may have the 1, 0, right? 1, 0 just corresponds to 1 plus 0 times I, and this is a real number 1. And this vertical axis is called the imaginary axis. So this guy is called the, let me use another color. Imaginary axis, so this vertical axis. Because all the points on this vertical axis are just the pure imaginary number. For example, you may have the point 0, 3. Now let's see how we related this order pair to a complex number. So 0, 3 just corresponds to 0 plus 3i. So this is equal to 3i. And this is a pure imaginary number. And given this complex number A plus BI, we can find the absolute value of a complex number. Let's first recall how we define the absolute value of a real number on a number axis. So suppose we have a number 9 like this. So this is origin, and then this is 2, and this is negative 2. Then the absolute value of 2 and also the absolute value of negative 2 are both equal to 2. And this 2 is just the distance between this point or this point to the origin. So similarly, in a complex plane, we may define the absolute value of a complex number as the distance between this point and the origin. Now let's go to the next page. So we define the absolute value of the complex number A plus BI. And this is just the distance between the point AB and the origin 0, 0. So you have the A minus 0 square plus B minus 0 square. And then you get square root of A square plus B square. So actually, this guy, generally, we use R for it. And this absolute value is called the modulus of this complex number. So it's called R. This is the modulus of complex number A plus BI.